You know, all we seem to hear about today is how humans are affecting climate. But there are many other factors that can affect climate, and that's what I'll be talking about in today's video. Well, one factor in particular, and that is plate tectonics. How plate tectonics or tectonic events in Earth's past have caused major global climate change. So starting with the very basics here, what is plate tectonics? Well, plate tectonics is the movement and interaction of Earth's lithospheric plates. Lithosphere is not, equivalent to Earth's crust. It includes Earth's crust, but also part of the uppermost mantle. But the lithosphere is what makes up the actual tectonic plates. And lithosphere that includes oceanic crust is denser and behaves differently than the lithosphere that includes continental crust, which is less dense and typically overrides plates like oceanic plates that go and subduct underneath continental crust. So there's these plate boundaries, and all the lithospheric plates on Earth, which are outlined in this map here, kind of interact and push and pull against and from each other. And these interactions can affect climate over geologic time. And in this video, I'm going to be listing 5 major instances where tectonic activity or a specific tectonic event has greatly influenced global climate. However, I do want to note that plate tectonics is just one of many factors that influences climate and causes climate change over time, and other factors include atmospheric compositional changes, things like greenhouse gas concentrations, for example, solar radiation, and differences in the distribution and amount of solar radiation received by Earth, which can be caused by things like astronomical factors. In other words, Earth's orbit, changes in Earth's orbit around the sun can change the distribution and amount of solar radiation received. Biology itself, life itself, can affect climate and has affected climate in big ways in Earth's past. For example, when photosynthesizers evolved and they produced oxygen for the first time, which hadn't really been around on early Earth, and that majorly changed the atmospheric composition. And so all these factors are kind of connected, and they greatly affect climate together. It's not a system where one can really happen without affecting the other, so they're all very interconnected is the point. Also note that plate tectonics is something that takes a freaking long time. These plates are moving around, but very slowly on geologic timescales, not at all close to human timescales. We can actually track the movement of the plates on Earth today, and we see, they're moving, I don't know what the actual rates are, maybe like a centimeter per decade. I'll look it up and actually put it on the screen here if I find the average plate movement speed, but it's very slow. So any actual significant movement and interaction of plates takes a very long geologic time, which means that it causes climate to change on a much longer timescale than other factors that might cause faster acting effects, such as changes in greenhouse gas concentration, for example. Any atmospheric compositional changes tend to much more quickly affect climate or change climate than plate tectonics, because plate tectonics just takes a long time to do anything significant. And for this reason, plate tectonics is actually never or typically not the sole cause of events like mass extinctions or other catastrophic events in Earth's history, because slow change, I've talked about this many times in my videos, slow change does not harm life as much as fast change. That's why, warmer periods in Earth's history, like the Mesozoic, for example, people always say, well, it was much warmer then, so why are we worried about it becoming warmer now? Well, it's the rate of change that's dangerous, not the actual magnitude of the change, not the actual magnitude of the warming. The rate of warming or cooling or whatever it might be tends to be harmful to life because life at the time evolved to those conditions. So if there's a gradual change over geologic time, potentially caused by plate tectonics, life tends to evolve, adapt, and be fine. But if it's rapid and there's no time to evolve or adapt, then life will die, and that causes mass extinction events. But plate tectonics has been the trigger for certain climate changes that eventually lead to mass extinctions, but it's never the sole trigger or sole cause. So the first example of a major tectonic event that caused a major climate change event in Earth's history is way back early on Earth, around 800 to 750 million years ago, when the supercontinent Rodinia broke up, and this caused major climate change because it greatly increased the rate of continental weathering at the time, which, if you've seen any of my climate discussing videos, I talk about how weathering and an increase in weathering rates specifically causes an increase in the rates of carbon burial, which causes major typically cooling because it decreases the amount of atmospheric carbon available and it increases oxygen. So it causes cooling in association with oxygenation events, typically, if it's like a big enough event. And this was. The reason that continental weathering, specifically silicate weathering, the weathering of silicate minerals like basalts or other volcanic rocks, increases the rates of carbon burial is because it greatly increases the flux or amount of transport of ions like calcium to the ocean, which react with carbonate and form calcium carbonate. And that greatly pushes the equilibrium of CO2 versus carbonate minerals in the ocean toward the carbonate formation side of things. I have a video talking about that equilibrium reaction recently, and I'll link it to the top right. But basically, it pushes it toward carbonate formation rather than carbonate dissolution, which leads to more CO2 in the water. And that causes a great decrease of carbon dioxide specifically, in the water as well as the atmosphere, because it takes a lot of that to form these rocks, and then they get buried and stay in the rock record for a long period of time, which decreases atmospheric carbon for a long enough time to cause major cooling. And another thing that weathering facilitates is primary productivity in the oceans. In other words, things like algal blooms, which greatly increase the rates of organic carbon burial. So not only are you getting inorganic carbon precipitating, minerals forming and becoming buried and stored in the rock record, but also organic carbon deposits are becoming buried and stored in the rock record. And that's leading to an overall decrease of carbon in the atmosphere and ocean, leading to cooling and oxygen rise, because typically the major sink for oxygen, or major way that oxygen is used up, is to oxidize organic carbon. And if it's all getting buried, or a lot of it's getting buried, it's kind of escaping that oxidation, leaving behind more oxygen in the oceans and atmospheres. So anyway, this contributed to a major cooling and oxygen rise period in Earth's history called the Neoproterozoic oxygenation event, which I have a video on, and I'll link to the top right for you. But another reason that Rodinia and its associated tectonics eventually led to an increase in oxygen in the atmosphere was because it existed for a long time, and during this time it had somewhat of an insulation effect that increased the mantle's temperature beneath the continent. So it was a supercontinent, and it's again lithospheric are the plates, the lithosphere, and then below the lithosphere we've got the rest of the mantle, and the mantle temperature beneath the continental mass was rising, and surrounding the supercontinent were a bunch of subduction zones. So again, oceanic plates subduct underneath continental plates, and this actually enhanced the heating effect that was already going on underneath the continental landmass, because the subducting plates prevented any lateral mixing. And so this lack of mixing not only caused this, weird heat distribution, but also led to the lack of reduction of the mantle material that was being brought down in the subducting plates. In other words, that just means that this oxidized material from the surface, which was oxidized by compounds like oxygen and other oxidized things at Earth's surface, didn't become reduced again. And those are just fancy chemical words for like having more electrons versus not having a lot. Things at the Earth's surface tend to be oxidized. Things below Earth's surface tend to be reduced because the oxygen and other oxidized compounds don't get down there. But subducting plates do bring them down there, and typically they get remixed and re-reduced, and it all comes back to a relatively reduced state, and then it's brought to the surface and oxidized. But in this case, it wasn't. And so the volcanism that resulted from the subducting plates, as shown by this figure here, basically was bringing back up oxidized magma and gas. And so it was already oxidized, and then it was extruded out of these volcanoes, and it was again expelling the already oxidized gas, which again also increased the amount of oxygen in the atmosphere, because oxygen was not then being used to oxidize the gas, which it typically is with volcanic gas, because it was already oxidized. So all that is to say, Rodinia and its involved tectonics led to this Neoproterozoic oxygenation event that happened to occur right before the explosion of animal life in the Ediacaran and Cambrian. So it was likely a big driver of that. So this tectonic event here with Rodinia and its breakup is really key to animal evolution. So it might seem like something that was just geological or whatever, but all of these things are combined and linked, and it then led to something that was biological and biochemical. And so all of these things are very linked is the point, and I think it's incredible, and I hope you do too. The second major tectonic event I want to talk about in this video that led to major climate change was the formation of Gondwana. Rodinia broke up and then led to kind of another intermediate supercontinent called Pannotia, which then kind of broke up and led to Laurentia and Gondwana and Baltica. These were kind of the three major continental landmasses after Pannotia broke up. But when Gondwana moved over the South Pole, or kind of positioned a little bit more over the South Pole in the Ordovician period, it contributed to the cooling event that kicked off the Ordovician mass extinctions around 460 million years ago. There's three major reasons why this caused cooling. One, glaciation spread just due to its southern position, but this also led to a decrease in sea level, which exposed more land and increased weathering rates. Again, increasing weathering rates lead to more carbon burial, leading to cooling. But another thing that contributed to the increasing weathering rates was the movement of continents through the intertropical convergence zone, which increased how much rainfall was falling on the continental landmasses, which, rain increases weathering greatly and chemical weathering and transport of those ions to the water where they react and precipitate carbon-bearing minerals. So this Gondwana movement / increasing weathering rate event led to this cooling, but these extinction events were associated with two pulses of extinctions and climate change events. One was the cooling and the second was a warming pulse. And so if you want to know more about how the Ordovician mass extinctions progressed and what, climate changes led to what climate feedbacks that caused the next pulse or whatever, I talk more about that in my Ordovician mass extinction event video, which I'll link to the top right if you want to check it out. The third major tectonic event or events that led to major climate change are collisions involving Laurentia. So yes, we talked about Gondwana. It was an amalgamation of a bunch of big land masses today and was huge throughout the entire, from about 500 million years ago to 300-ish million years ago when Pangaea started forming. But it was a major thing that had major importance and control on climate throughout the early to mid-Paleozoic. But Laurentia was not small by any means, nor was its effect on climate. It underwent several collisions throughout the Paleozoic, which eventually closed a major ocean basin, the Arctic Ocean, and formed the Appalachian Mountains. The closure of this ocean and the formation of this major mountain range greatly altered atmospheric and oceanic circulation, and thus global climate. But this was a stepwise process. There were multiple collision events that eventually led to the ocean closure and the mountains formation. And these events included the Tectonic orogeny, the Akkadian orogeny, and the Alleghenian orogeny. I hope I'm pronouncing Tectonic better. I don't know. I had a commenter tell me how to pronounce it more correctly, and I hope I'm getting it right, but pronunciations through text are difficult to comprehend, so let me know if that was correct this time. In any case, this first stage of mountain building involved the collision of Laurentia with an island arc. This second stage also involved the collision and accretion of an island arc onto Laurentia, and the third stage finally set in the collision of Gondwana with Laurentia, which was the event that led to the beginning of Pangaea's formation, the major supercontinent that existed thereafter until the Mesozoic when it began to break up. Which brings us to our our fourth tectonic event that affected climate, and that is the formation of this major supercontinent, Pangaea. Pangaea began forming around 320 to 300 million years ago as Gondwana and Laurentia collided, and this actually led to the largest ice age of the Phanerozoic eon. In other words, the largest ice age within the last 500-ish million years ago, and some major mass extinctions at the time. Not one of the big five mass extinctions, but a mass extinction event no less. System changes, and because the Carboniferous was previously and mostly known for its globally widespread coal swampy environments, climatic drying or increased aridity that the supercontinent Pangaea brought with it greatly contracted these coal swamps, and this contributed to mass extinctions, but it also did eventually cause enough of a decrease in carbon burial to bring us out of the ice age and into a period of warming, which eventually led to the greatest extinction event of all time, or greatest extinction event of the Phanerozoic eon at the end Permian, which was not only caused by the warming due to the contraction of coal swamps, but also major volcanism, which I talk about in my video about that extinction event, which I'll link up here if you want to check it out. Pangaea then began breaking up in the latest part of the Permian around 250 million years ago. This might have actually contributed to triggering the volcanism that I just mentioned that caused, or in part, caused the climate changes that led to the greatest mass extinction event of all time at the end of Permian. But there's also other hypotheses regarding how this volcanism was kind of triggered and started in the Siberian traps. But it's possible the early rifting of Pangaea did help to trigger these massive volcanic eruptions. However, Pangaea did remain relatively intact throughout the Triassic period after the end of the Permian, so it didn't do that much rifting, if any, at the late Permian, early Triassic time. But later in the late Triassic or end Triassic, around 200 million years ago, that is when the real rifting began in the central Atlantic, where now the mid-Atlantic ridge is. The faults, or kind of breaks and slippage in rocks in this region due to this tectonic rifting or tectonic extension or breaking apart of the plates, allowed magma to seep through and form dikes and sills. Dikes and sills are when magma comes up, and dikes are like these vertical chutes of magma that come up and then cool like just below Earth's crust, and then they're uplifted, and we can see there was like a chute of magma that went through these rock layers. Or a sill is kind of the same thing as a dike, but horizontal. It kind of seeps through horizontal rock layers. And an example of a sill here is one of the largest sills in the world, the Palisades Sill along the Hudson River, which is actually part of the Central Atlantic Magmatic Province, which formed and erupted during this time in the end Triassic because of the rifting apart of Pangaea. This major volcanic activity greatly increased carbon dioxide in the atmosphere, led to warming, led to ocean anoxia, and actually greatly contributed to the end Triassic mass extinctions, another major mass extinction event that I have talked about, and I'll link the video up here to the top right for you. I'm not trying to just send you to all my other videos, but I have talked about this, and if you want to know more, there you go. But this breakup did not just lead to kind of bad climate changes that led to mass extinctions, but also led to, eventually, a great diversification of life in the Cenozoic. So the breakup of Pangaea, ultimately, in the long term, and not the initial volcanism that it caused, but the splitting of the continental land masses, ultimately led to more speciation, in other words, more geographical isolation of species, and therefore the formation of new species over time for mammals in the Cenozoic. And as we all know, after the end of the non-avian dinosaurs, after the Mesozoic, the mammals took over in the Cenozoic, and a large part of the great diversification of mammals during the Cenozoic, and still today, is because of the big split in continental land masses that occurred, allowing there to be more and more rapid speciation. So those are 5 examples of how plate tectonic events in the past have contributed greatly to affecting global climate change. But why is it so important that we study how plate tectonics in the past has worked and how it's affected climate? Well, it's basically key for us to understand how plate tectonic works on modern Earth and how these tectonic events and this tectonic movement that's currently happening might affect climate or other Earth processes in the future. And the way that we study this involves a lot of data analysis, probabilities, statistics, modeling. In this video, we are going to be talking about 5 more times that tectonic events have caused major climate change. So in today's video specifically, the 5 tectonic events that I chose to discuss that have majorly affected climate in Earth's past ended up being largely involving opening and closing of ocean basins. 3 of the 5 events actually involve, or maybe 4 of the 5, we'll get into it, but they involve opening or closing ocean basins in some way. And this was just by coincidence, but it does speak to the fact that opening and closing of ocean basins really does heavily lead to changes in climate. For example, by changing oceanic circulation patterns, which, in turn affect atmospheric circulation patterns, and this can pretty significantly affect global climate. And I just wanted to briefly cover the fact that the opening and closing of ocean basins is typically summarized as the Wilson cycle in terms of plate tectonics. So what happens is you start with a stable craton, a stable, continental landmass, and then you might have rifting occur where a boundary forms because it's stretching apart, it's ripping itself apart. And this could be due to a lot of things. Typically, this kind of thing starts with plumes or hot spots in the mantle that kind of come up from the mantle and cause heating and pulling apart or thinning of the continental lithosphere, which then causes it to then start to rift apart. And this can typically start as like a point that then spreads out as, the plume comes up and causes that expansion. And that eventually leads to a full boundary of extinction where the plates are pulling apart once they kind of form into 2 different plates. And you can see with the arrows here the movement of the plates apart from one another causing this rift zone. And then eventually that can form an ocean basin because the lithosphere stretches out and thins out so much that, there's a basin there and water fills it, and then it keeps going and getting bigger and bigger and eventually can become an ocean. So that's the opening of the ocean, but then that ocean basin can also close, and closing of ocean basins typically, not typically, always occurs due to subduction. Subduction, again, is where oceanic plates will subduct under or kind of go beneath continental plates because they're more dense than continental plates. The reason that subduction is typically initiated is because there's some sort of plate boundary or boundary in which the forces are pushing an oceanic plate against a continental plate, and that will eventually force the oceanic plate under the continental plate. In this example, we can see that this started as what's called a passive margin, where the continental landmass passively gradually turned into the oceanic plate because of that rift zone that eventually formed the ocean basin. However, it turned into an active margin where the plates were then pushing against each other and the oceanic plate started to subduct under the continental plate because of some sort of forces. Probably, maybe this continental landmass hit another plate behind it and it caused it to stop or push against this oceanic plate because this oceanic plate was coming out of this mid-ocean ridge and pushing toward that direction. So that eventually led to convergence or a convergent boundaries where they push against each other, and that force toward each other led to the oceanic plate subducting under the continental plate, which then eventually closed the ocean basin. So that then led to, again, those continental land masses kind of merging into one, which then can be eroded down again into a stable craton. So you have this huge cycle that can repeat itself and has repeated itself with many ocean basins throughout Earth's history. And these events have caused major climate change events throughout Earth's history, and those are some of the examples I'll be giving in today's video. The first major sea or ocean basin we'll talk about that opened during the Mesozoic is the Tethys Sea. This sea formed between Gondwana and Laurentia as they rifted apart, breaking up Pangaea, the supercontinent that formed just before the Permian and contributed to the Great Dying, one of the largest extinction events of all time. I talk about how the formation of Pangaea and its breakup affected climate in my first How Tectonics Affects Climate video, and I'll link that to the top right if you're interested. But basically, the formation of this sea greatly affected ocean circulation and thus climate. When the rifting in the mid-Atlantic ridge began, in other words, when Pangaea started breaking apart, Laurentia, the continental landmass that included, like the North American craton, started rifting or moving northward, and Gondwana, which included South America, Africa, Antarctica, India, Australia, those landmasses all clumped together, and Gondwana started moving southward, breaking up Pangaea and forming the Mid-Atlantic Ridge, which started forming the Atlantic Ocean. But early on, this basin, when it started to form as a basin, was filled in by spillover from the Tethys Sea, which, because of Pangaea's really dry, arid climate, largely was evaporated when it spilled over into this relatively new and shallow basin. And this caused really extensive evaporite deposits, salt type deposits that form when water, evaporates, leaving behind its salts to precipitate. And that was mainly because, like I talked about in the previous video, Pangaea led to a really dry climate because it was such a big and, conglomerated continental landmass that much of the land, one, was kind of uplifted away from the sea and so far inland away from the sea that much of the land was really dry. And there's a really arid climate, especially of like central Pangaea, which was the part breaking apart, led to the evaporation of anything that spilled over into the early Atlantic basin. But eventually it did lead to the more stabilized sea and obviously eventually, over a lot of time, the Atlantic Ocean. However, the opening of the Tethys Sea wasn't the end of the story. The Tethys Sea also closed during the Mesozoic in the Cretaceous, which formed the Alps and nearby mountain ranges all along this convergent boundary where Africa was moving toward Eurasia at the time. And these newly built mountain ranges, obviously any mountain range that's, high, affects atmospheric circulation and thus can affect regional, but also, if large enough, can affect global climate. This wasn't the only thing that the closure of the sea allowed, though. It also allowed the exchange of plants and animals across this land bridge that had formed, which likely also altered regional climates. Like I talked about, life is a major thing that can affect climate. And so this land bridge allowing the exchange of animals and plants across this boundary really did affect the regional climates of either continental landmass. The closure of the sea also likely contributed to the warming trend during the Cretaceous. It did so by, one, reducing the capacity of the ocean to absorb heat, which thus increased surface temperatures, and two, lowering the solubility of CO2 in seawater due to changing ocean circulation and temperature. Again, however, this was by far the only thing contributing to the warming during the Cretaceous, especially by the end of the Cretaceous, where there was a big spike in rapid warming due to meteorite impact and the climate changes associated with that. But this is one of the potential contributing factors to this long-term warming trend in the Cretaceous. The second tectonic event we'll talk about in this video that had a major effect on climate is intimately related with the Tethys Sea and when it was spilling over into the newly forming Mid-Atlantic Basin, and that is the Atlantic Ocean. The Atlantic Ocean, like I had shown previously with that Mid-Atlantic Ridge, started forming during the breakup of Pangaea, and when the Atlantic became like a full-fledged ocean, it greatly affected ocean circulation, obviously. I mean, imagine if the Atlantic Ocean just poof wasn't there tomorrow. I mean, it's such a big part of modern ocean circulation, and this happened over a really long time, but now it is finally a huge ocean basin and still spreading, still getting larger, and so it is really integral to the ocean circulation system that is currently occurring on modern Earth and, controlling a lot of climatic factors on modern Earth. Whereas before it had split, ocean circulation was very different because it was always kind of limited to going kind of around Pangaea and, within the Tethys Sea area, but not getting in between the continental landmasses of Pangaea. Significantly, the rifting in the North Atlantic allowed warm equatorial waters to flow north, releasing heat to the atmosphere, and this contributed to the cooling trend during the Cenozoic. So right after the closure of the Tethys Sea contributed to the warming trend in the Cretaceous ended with the meteorite impact and the big warming spike and extinctions and all of that, and then it bounced back to a relatively, cooling trend throughout the Cenozoic, which was in part caused by the formation of the Atlantic Ocean. Rifting in this region also caused volcanism and increased silicate weathering and carbon burial, thus decreasing CO2 levels. Like I talked about in the previous video, anytime you have increased silicate weathering rates, the weathering of silicate minerals like volcanic basalts or other igneous rocks, this contributes to carbon burial or increases the rate of carbon burial by increasing the rate at which ions like calcium are transported to the ocean, which can form calcium carbonates, causing the storage of carbon long-term in the rock record. It also increases the flux and rate at which other ions like potassium, phosphorus, nitrogen are transported to the ocean, fueling as nutrients. They fuel primary productivity or things like photosynthetic algal blooms, which increase the organic carbon burial rate and also cause the storage of carbon long-term in the rock record. So the storage or taking of the carbon from the atmosphere and ocean and storing it in the rock record thus decreases CO2 levels in the atmosphere and causes cooling trends. But don't get any ideas. This is a very long-term kind of effect that doesn't cause rapid change. So it's not like, well, it can help us offset the current increase in CO2 levels in the atmosphere, but not on a time scale that would compete with the current increase in CO2 levels. So it's not like it could really compete with that. It would long-term, but not in the short term. The Atlantic Ocean also, when it formed, provided new marine environments where more organic carbon burial could take place. So not only was there increasing weathering rates leading to more potential organic carbon burial favoring conditions, but also there was a new ocean available where that could take place, because that doesn't happen on land. You only get organic carbon burial or carbon burial in general in marine environments, or aquatic environments at least. I should mention that when Pangaea was forming, we did have the really coal swamp rich world of the Carboniferous, which led to a lot of organic carbon burial, and that was in terrestrial environments, but again, they were aquatic, and these swamps greatly dried up in the Permian because when Pangaea kind of took its full form, it really obviously, like I mentioned earlier, increased the aridity of the continental landmass and therefore greatly decreased the amount and distribution of coal swamps around, and that decreased the carbon burial rates in such environments. The cooling associated with the formation of the Atlantic Ocean also then triggered further cooling because it led to positive feedback mechanisms, which are climate mechanisms in which one climatic trend causes the exacerbation of that same trend. So cooling causing more cooling, or warming causing more warming. The reason cooling can cause more cooling is because once cooling takes effect and causes especially things like glaciation at the poles, or a pole at least, that leads to the increased albedo effect of Earth, which basically means like increased solar reflectivity, which means that more solar radiation is reflected rather than absorbed by Earth, therefore cooling Earth even more, which leads to more formation of ice or spreading of glaciers, and therefore more reflecting of light, and therefore more cooling. That is the positive feedback that took place when glaciation finally started to form in the Cenozoic at the South Pole in Antarctica. The third major tectonic event that led to climate change that we'll talk about today is the formation of the Indian Ocean, which also took place or started in the Cretaceous. The opening of this ocean greatly altered, again, ocean circulation and heat transport within the ocean and thus atmosphere, and therefore also global climate. And I know what you're thinking. India actually hadn't hit Asia yet. It was headed up there, but it hadn't collided with Asia yet. So the Indian Ocean already started to form before India collided with Asia. Also, with these reconstructions of paleogeography at these different times in Earth's history, you might be noticing that the Tethys Ocean looks to be kind of where the Indian Ocean is today, or kind of took over where the Tethys Ocean was then. So what is the difference between the Tethys and Indian Oceans, and what marked the transition between the two? This is where you need to understand plate tectonics to really understand these pictures, because what you might see if we go back here is India is, kind of tied up in the big clump of continental land masses known as Gondwana down here during the Jurassic around 150 million years ago, but then around 94 million years ago in the Cretaceous, it started to break apart and move toward Asia, or Eurasia at the time, which eventually it collided into, which is where it is now. And here we can see it continued moving that direction right before it hit. But it is not as though India was just kind of floating on the water there to get to Eurasia. That is not how plate tectonics works. Actually, the Tethys Ocean basin was closing as India moved north due to subduction of the Tethys Ocean tectonic plate underneath, that's what those arrows mean, the subduction of that oceanic plate underneath the Eurasian plate. India was actually, rather than moving, or driving the movement, it was actually kind of just along for the ride of this subduction and movement of these plates toward Eurasia. So what did drive this movement? Well, it's important to note a couple things here about plate tectonics. One, subduction, once it's begun, the oceanic plate is subducting under the continental plate, and there's something called slab pull, where the subducting plate is kind of pulled under the continental plate at that point because it's getting into the mantle, and convection continues to kind of pull it or drive the subduction because it's just pulling on the slab, basically. That's kind of what we call it when it's subducting, is like a slab, subducting slab, and it's being pulled, basically, pulled under. The other thing that drove this movement was from the other direction. So in the front here, we have the subduction pulling this whole plate toward Eurasia, including India, and then we also had the pushing of India toward Eurasia because we had other ridges, other oceanic ridges where seafloor spreading was occurring. And that's kind of what this map is showing, is basically the age of the ocean's floor using radiometric dating, which show that the youngest material comes out from the spreading mid-ocean ridges, and we can see that new material was coming out of these ridges, pushing things in that direction in association with the slab pull. And what drives mid-ocean ridges and seafloor spreading is, again, mantle convection. So everything comes back to convection in the mantle and this, heat transport of the mantle and just mixing of the mantle, which, leads to all of this plate tectonic activity. So why did India stop when it reached Asia? Like, shouldn't the subduction have continued? Well, actually, continental crust does not subduct like oceanic crust does. It's just too buoyant. It's not dense enough, and it just, when it hits each other, it just instead smooshes together really hard and forms these really huge and high mountain ranges. And that's why the Himalayas is, the highest mountain ranges, or has some of the highest mountains, is because it's continent on continent convergence. Anytime you have mountains that form due to ocean subduction underneath a continental crust, you'll get mountains, but they won't be quite as high as you get when you get continent on continent convergence. And this, like I mentioned, leads us to the Himalayas, which is actually our fourth major tectonic event that led to climate change. So the previous one was about the closure of the Tethys Ocean. So remember, the Tethys Ocean plate, the oceanic crust that the Tethys Ocean was over, covering, or the water of the Tethys Ocean was covering, that crust got completely subducted and completely closed when India hit Asia. And then behind the Indian continental landmass came the Indian Ocean, which was a whole different set of crust. So the difference between the Tethys Ocean and the Indian Ocean, to answer our previous question, is the crust underneath it is completely different. It's new because it spread from that mid-ocean ridge behind it, whereas the Tethys Ocean crust that was there has been fully subducted under the Eurasian plate. There are some remnants of the Tethys Ocean or seaway still around, like the Mediterranean Sea and other seas in that region, but the big ocean basin was closed. Then we had, again, the collision that led to the Himalayas, which completely changed the climate of India. As we saw, India was kind of this floating landmass, which had these seas covering where now the Himalayas are. Can you imagine that? It had shallow seas and this, carbonate production environment where it was kind of like this destination beachy environment. And now it's this thing covered in these huge mountains. It's just such a huge shift in climate due to plate tectonics. This collision also led to the formation of the Tibetan Plateau, which altered atmospheric circulation greatly because it's so tall. And this led to the Asian monsoon system, which significantly impacts regional climate in that area. Lastly, the fifth tectonic event or events that eventually led to or kind of triggered the shift into our modern ice age that we're in today is one, the formation of this kind of seaway passage between South America and Antarctica occurred around 34 million years ago, and this led to a major shift in ocean circulation that kind of triggered the modern glaciation period, because before opening, warm waters from the Pacific circulated around Antarctica, which obviously kept it somewhat warm, preventing major glaciation, whereas after the Drake Passage formed, it allowed the Antarctic circumpolar current to become, isolated around Antarctica, basically isolating that climate to kick off the Ice Age and the major glaciation period that, started around this time. The second major trigger of the modern Ice Age, more recently around 3 million years ago, was the formation of the Isthmus of Panama, which led to the Great American Biotic Exchange of flora and fauna, plants and animals between these two continents, which was major for biodiversification, and we know that life can significantly influence regional climate and global climate, as I talked about previously. But this wasn't the only thing that this land bridge caused. It also led to a major shift in ocean circulation in the Atlantic and Pacific Oceans, which impacted global climate and contributed to the further triggering of the modern ice age. So the kind of thing that kicked off the general cooling trend from 30-ish to 3 million years ago was the Drake Passage, which then the formation of this land bridge kind of dropped us into the modern ice age from 3 million years ago to present.